All right. Hello. Welcome everyone who's joined. All right. I guess today I will be coding a little bit in the NES and Game Boy emulator again, and we'll be focusing on scaling algorithms because the screen is a little bit it's not a perfect match for the NES emulator, so we need to scale it a little bit. And it turns out that the original stock firmware actually stretched out the frame buffer a little bit. So that's what we're going to look at today. And I guess I can do a quick update of what's been going on. So someone called Jake has been um, tracing the PCB completely by this time. So we now have a full, complete PCB retrace of all components and all traces, which is really wonderful. The only thing missing now is actually identifying exactly which parts we have. Most parts have been identified, but the audio codec has not been identified. So we don't really know what this is. But I guess that will happen eventually. We have 0 bricked units that I know of at least, which is really good. So there has been a lot of people joining the Discord and asking for help and so on. But eventually we have managed to get a successful backup procedure of everyone who's been asking, at least that I know of. So that's really good. I'm really happy about that because I was worried that people were gonna have problems and that we might end up, bricking people's devices and so on. But that has not happened, which is really nice. I mean, to be fair, it's SWD. It's a very standard STM32 microcontroller, so we shouldn't really be able to brick people's devices. But it's in case something works and something doesn't, and so on. It's always a little bit scary. So yeah, but anyway, it seems things work. Another scary thing is the power management, where we actually managed to track down a very strange issue where if you don't connect the battery, in some cases when booting up, the 1.8 volt rail could have 4 volt, which is really not good. And we got some help from Yoxan. And we managed to track it down all the way. So the conclusion was basically that the switching power regulator gets stuck in the on switch position. And there are 2 ways to fix it. One way is to add a big capacitor to slow everything down a little bit, have some buffer in the whole system. The other is to add a sleep in the power on sequence. So that's what we're doing in the firmware. So we have a sleep. A sleep solved this issue. So I managed to find that the sleep worked around the issue, but I couldn't explain why. But now we actually have an answer. So if you want to see the details and how we tracked it down, you can head over here to the base project and then issue number 5. So yeah, this feels good because having high voltage when you're not supposed to have high voltage, that's not very nice. So yeah, that's basically the 2 major updates, I would say. Yeah. So I guess I can head in and start coding. I don't have much more to update. There's always stuff going on, but yeah, I don't have anything to report right now, I think. So let me just find the link that I'm looking for, and then let's check it out. So yeah, a few days ago, or maybe it was yesterday, I don't remember. 2 days ago, I asked a question on Twitter where I'm looking for a RGB 565 linear scaling algorithm that is optimized for ARM M7, and it just so happens that the performance whisperer had a perfect match. So that was really unexpected, to be honest, that someone had an optimized scaling algorithm for exactly this platform. That was cool. So let's check it out. So it is this OpenMV project, which I've never really heard about. So it seems to be like an embedded camera or some sort of video project. Yeah, so the actual code is located over here in the draw functionality. So I have checked this project out, so we can open it in an editor instead and see if we can look at the code together. Try to understand it. There we go. All right. So first of all, where are we? What is this? It's a huge function. It probably handles scaling for everything, I would assume. Thanks for the photo. Okay, lib draw image. So question is, should we try to build this or should we try to extract the code? I don't know. It's probably easier to just extract the good bits from this rather than try to port the whole function. There's no real, because we only care about one color format, and we probably need to do some custom adjustments anyway for our project. But just to get an understanding of what we're dealing with, I've literally never seen this code before, so let's try to understand it together. So they have a struct with a width height, bytes per pixels or bits per pixels. We'll see. I guess it's bytes per pixels. Yeah. And then either pixels or data, but it's a pointer. Okay. So nothing strange. This should be easy to understand. Destination x start, so that is where we are supposed to start writing. And in our case, we actually want to care about this because we have the horizontal pad where we are actually splitting into a frame buffer with an offset and not from the very beginning. And then y start, yeah, in our case, that will be 0. X scale and y scale. So these are the scaling factors. So in our case, the x scale will be something like that will be 307 divided by 256. So almost 1.2. We are scaling up, yeah. And y scale will be 1.0. Rectangle Royce, I guess that is region of interest. So that is if we perhaps want to cut something from the, like if we want to crop the source image, I would assume, I don't know, still guessing. RGB channel alpha. Okay, so is this operating on one channel at a time? I don't know. Let's find out. And then we have alpha as well. Yeah. We have a color palette. That is good because we also have a color palette. Our input data is actually in an indexed format. We have 64 different colors on the NES palette, and it's mapped to 256 array because the frame buffer actually contains some extra bits for if it is a background or foreground tile or sprite. So okay, so this might be useful. And then hint, image hint, what is that? That is which sort of, which kind of scaling we want to use. And in our case, we want to use the bilinear. So that's interesting. Then we have a callback, which is probably being called for every row when each row is finished. Yeah, that seems reasonable. Okay, so now we understand the API. So first we do some calculation to figure out if we are flipping the image. Oh yeah, right. So if you're scaling negatively, you want to flip it in some axis. But you don't want the resulting image to appear out of screen, so that's why you probably have this destination Y. Yeah, exactly. So it's operating on the other direction. Yeah. Okay. Oh, this is interesting. What is a fast floor? How is that implemented? Let's not dig into that. Just assume they have a good floor function. All right. Yeah, okay, let's continue. Right, so just a few early exits here where we identify if we have to do anything or not. Center source if hint is set. All right, so some basic layout. Clamp X to image bounds. Right. Yeah, so just a bunch of business logic to make sure that our inputs are sane. Do we need to do anything here? No. Destination delta X. Right. Yeah. But we don't have to care about flipping. We want it to be just an image, like a one-to-one in the axis. Apply region of interest offset. Right, so that is what I was expecting. So this is where it sort of reads pixels from. So it's offsetting the input buffer. Okay, so this explains that it is a fixed point implementation. There are no floats in the actual image processing, and the reason for that is probably because converting back and forth between integers and floating points are expensive. It's expensive to do that because you need to shuffle around your registers and convert back and forth. So even if the math to actually process images with floating point, because we have a floating point unit, but so even if that processing is fast, we need to convert back and forth between the color spaces. So basically from indexed color space to a floating point sort of intermediate values, and then finally convert it out to 565, and all of that will be a lot of shuffling around. All right, so let's continue. So here we actually, so this might actually be quite important for us to set up in our clone of this. Yeah. So let's try to understand what's going on here. So destination X reset. So this is the initial value. So if you have a destination, it will set it to. All right. So if it's a negative one, it's this one. Otherwise, it's this one. Yeah. So in our case, it will be the destination X start, which is 0. No, actually not, because we're actually writing into an offset. But yeah, we can deal with those details later. And then we have the source X fraction, where we take Yeah, so this is 16 bits divided by x scale. And in our case, this is our x scale. So no way. Okay, right. We're creating two variables. The comma operator always throws me off guard. So we create two variables. This is starting to look interesting. Okay, so I guess they're operating on something called 16.16 fixed point. So we have 16 bits of integer part and 16 bits of fractional part. So just to make a quick explanation of what this is, in case you don't know, when you represent 1 as an integer, it is literally 1 in your in the registers. But in 16.16, the integer part will be shifted left with the 16 positions. So this is the representation of a 1 in 16.16. So let's say 1.5, what is that? Yeah, then you take 1, shift that, and then you, I don't know really how to do this in a good way, but this is basically how you would do it. So this position here is the integer part, and then this is the fractional part. So in this case, we have taken the maximum value, like the whole integer part, which is this, this, and divide it by 2. So now we have this is 0.5 basically. And you can express that by just setting this bit. But anyway, that was a really bad and quick explanation on how fixed point math works. But yeah, that's basically it. So now from the looks of it, we're operating on 16.16 fixed point values. So what are we doing more? So we prepare this source X. Yeah. So what we do here is basically we prepare the scale. So what happens if we do that? Divided by X scale, and X scale was this. So just to see what we get this value. So this is less than 1 actually. And then they do like this. So let's just expand this. Okay, so now we have that, and then we have this one. We can actually copy this whole line. Okay, I'm not very good at Python, so maybe this will work. Yeah, so now we have the fractional part, which is less than OXFFF, and then we have this one. Okay, so I guess I don't really understand what this does. Yeah, let's try to understand that later. Okay. Oh, so they even have support for the DMH2D block. That is interesting. In case you're not aware, DMA2D is the built-in accelerator in the chip. But it's quite limited. So what it does mainly is it can convert between color spaces, and it can what's it called again? It cannot scale, but it can copy and blend two frame buffers. So you can have a background and a foreground layer, and it will blend them together in hardware. So it's basically free. No, sorry, actually, that's not true. So the DMH2D, it can do some stuff, but it still takes time. There is actually yeah, some PDF. So there are two different things actually. I mixed them together in my head. So there's the LCD driver, the LTDC, and LTDC is what handles the layers. So this is like the final step before the pixels reach the frame buffer. The actual no sorry the actual LCD. So this is the LCD driver. This is what outputs your pixels to the physical layer. And in here it can read from two different buffers and blend them together while outputting to the LCD. So this is 100% for free. So if you have two layers, you can blend them together, and that will be completely fine and cheap. However, there is a different block called the Chrome Art, also known as DMA2D, and that is what can do the memory or the color space conversion. So it explains a little bit here what it can do, pixel format conversion, and okay, it can actually blend. So that's interesting, but it is not for free because it has to operate at memory, like it has to read the memory and write memory. So it cannot be like O1, it has to be like at least ON, it has to look at each pixel. So it is not 100% for free, but it's also logical. Yeah, it wouldn't make sense for it to be completely free. But yeah, just yeah, now you know that. And oops, um, let's see here. Yeah, so this was the DMA 2D stuff. So this is kind of interesting. This shows that there is actually some DMA 2D stuff in this code, but I don't think we're gonna use them. Oh, okay, there's some spammer. Let me kick it. Let me kick it. I am too stupid to use Twitch. Like, I can reply to the spammer, but I want to kick the spammer. Why is it so hard? There we go. Okay, so now we don't have the spammer. So anyway, let's see what's going on. Yeah. So now we can continue. So this is actually where the fun starts. But yeah, this function is quite big. If the image is being scaled down by an integer factor, or slow mode if it's a fractional. Okay, so we're definitely in the slow slow mode because it's not an integer scaling. So yeah, what's more going on here? Binary. Oh, okay, so this is if it is if you only have 1 and 0 as a color. So like that. Okay, so can you fold? Yeah. oh, for once, I'm actually using the folding feature. I almost never use this feature in the editor, but now it's actually really useful. Okay, so yeah, we're operating at this color space, the 565. And how does this actually work? Holy shit, this is big. Um, mm, okay, so it's preparing some indexes. And the weight, okay, so right, so the weight is how important one or another pixel will be in the calculation. So basically the blending factor, I would say. Um, so what was this again? Okay, so it prepared a struct here that I didn't read. So let's read that. So imlib draw row data. Okay, so for each row we have some sort of right. So this struct is for the whole image with the full width and height and the pointer to the pixels. Right. So this is the full stride. And then we have the source bytes per pixels. RGB channel. Okay, so our RGB channel is probably a bit mask for each channel, I would assume. And then we have the palettes, alpha palette. Yeah. Okay. Doesn't actually contain any row specific. Okay, so that's what's happening here. Row setup. So what does that? Oh shit, this does a lot. Okay. Let's understand. So how many layers of macros? Okay. So we take the width, we multiply with the bytes per pixel because it's 565. Then we take the width times 2 times the height. Okay, so nothing strange. So this will return the number of bytes in the whole frame buffer. Okay. And then we have that divided by height. Okay, so this is just a way to get how many bytes a row is. Okay, fine. And then we allocate a buffer for that. And then in case we want to use DMA2D, we do some setup stuff. I guess we can skip that because I don't honestly think we will utilize that at all. Because we're not blending anything, we're just stretching it. So we can ignore that. Okay. And does some stuff with the alpha channel. I'm not sure what this is. It's probably a specific algorithm. Yeah, because we're not dealing with alpha channel at all, we don't have to care about that, I guess. Okay, so the row setup, it allocates the buffer and what more? it sets this stuff, which I think we can ignore. It does some stuff with the alpha channel, but we don't really need to care about that. Okay, so I guess we can just ignore this and just set up the row buffer. That's all, I hope. So now that's done. Cool. Yeah, so yeah, okay, now this makes sense. All right. Yeah, let's continue. So again, we were looking at the the row data and how that all fit together. So get row buffer, right? So then it just simply returns the row buffer data toggle. All right, it was a to indexed buffer. Yeah, exactly. And then it swaps between those. Okay. So it can operate on double buffering in case you have a DMA request. Makes sense. But in our case, we only need one. So okay. So now we have a destination pointer. What do we do with that? Yeah. Okay, so here it prepares some iterators. Okay, so it operates for each line and then for each column. Yeah, nothing strange. And here it iterates. It increases the index. Yeah. Okay, so here's the actual multiplication happening. So what do we do here? SMLAD. What does that even mean? I'm trying to understand what we're actually doing here. Source accumulator. Okay, so this is where we're reading from. So it's basically 0. So 128 minus 0. Okay. So this is basically telling us that we want to mix 100% with this pixel, I guess. So 128 shift left with 16, right? So are we operating at 8.24 now? And then we OR it with the right weight. The right weight comes from the fractional part, right? So because we are scaling up, yeah, and we actually, yeah, there we go. So this is the fractional part. So then we have basically 0 plus this, and we shift that 9 times. That looks like it will contain some value. Oops. Yeah, exactly. So we actually do have a right weight. So yeah, there we go. Then we have this weight multiplied with ty weight. And where did that come from? So for each y row, right? Okay. Q add 16. Okay. Is that actually implemented? I guess we have it. Nice. Do we have this? Okay, so is that an M7 function? Signed dual multiply add. Okay. Yeah, this is efficient, I guess. Okay, you know what? I'm just gonna try to fast forward a little bit. So it prepares the weights, and what does it do with that? This is a lot of code. Wow, some magic constants as well. I guess this is to mask out the colors. Yeah, RGB. Oof, and here's some even more optimized stuff. Okay. And here it's merging it. And here it's writing it back. Okay. Okay, but now I have at least a basic understanding of what we're trying to achieve here. Yeah. So let me just double check that I'm actually reading the right code. So line 4259. Okay, it was actually the wrong code. Okay, 4259. So what is the difference between this? Why did I end up there? So this function does way too much. Aha, okay, so this was the cropping algorithm. Okay, so let's look at this one instead. No, this is also wrong. Okay. So there's the hint bilinear, and that is bicubic. Okay, right. We only care about the bicubic one, bilinear one, because we don't want to look at that many pixels. That's gonna be too expensive. Okay. So, but at least we have read some code. We're getting into the whole mindset. 4259. Yeah, this is the code we care about. But that's still interesting. So yeah, let's read this. I can be a little bit faster, so it's not that boring. Okay, so again, the same principle for each row, for each column. So yeah, so just some bound checks. Yeah, so here it prepares the pointer where it should read from, and here it will operate on each horizontal pixel in that row. And here it prepares the, yeah, basically this little matrix or whatever you want to call it. So, okay. I think we can get rid of quite a lot of this code because we always know how we are looking. Because we're doing the same operation. We always scale up, and it will always be within a certain. We will always hit like one of these if cases. I think, maybe not actually, because when you get close to the edges, it gets a little bit nasty. Like when you're at the very last pixel, you don't want to look beyond that pixel. Okay. And here is the color mask. Okay, so it's actually operating on 2 pixels at the same time. You can see here, it's a 32-bit word with 2 masks, and that is because each color is or each pixel value is stored in a 16-bit value, so it's masking twice at the same time. And then here is the green channel and the blue channel. Okay, so as expected. Cool. This I don't know what it is. Okay, here's it's doing some magic here that I don't understand. And then there's a while loop again. So we're first in a while loop, and then we're in a do, and then we're in a while, and then we're in a do again. Okay, wow. Cache the results of getting the source pixels. Used to mix pixels horizontally. Okay, so now it's saving the look ahead. Okay, so this is actually really interesting. So it seems that it's actually caching the next line that it has already read and using that in the next iteration. That's interesting. But where does it cache it? That I don't know. Put on the destination row. Okay, let's just accept this. Okay, so this code is actually not that much to copy. It's only this. So, or actually it's this, yeah. So we need this plus some setup code. So let's, yeah, let's give it a shot. This is gonna be interesting. So just to give you so I'm actually gonna use the Game Boy emulator because it's smaller, so it's quicker to build. So let's jump in there and look at some blit function. So we have the blit normal and blit nearest, and then I'm gonna add a new one called blit bilinear. So I did a bilinear naive implementation. I can just show it to you, just so you can understand what's going on. There we go. So this is a naive implementation that is very sort of by the book and not optimized at all. So what we're doing here is, so this is the blit function. We take a bitmap, the source, and a frame buffer, the destination, and we calculate the scaling factor here and here, and then we operate just like the algorithm you just saw, just expressed a little bit differently. So for each vertical line and then for each horizontal pixel, we will be looking at the neighboring pixel. So first we look at the current pixel, and then we look at the next pixel. And yeah, this is also not very good at the very last pixel. It will go out of bounds. But anyway, it's don't think too much about this. This was just a test. And then this is the algorithm. So we're doing lerp, which is linear interpolation between RGB and RGB values, 2 separate RGB values. And then here is the factor. So how much of the left side or how much of the right side we want. And then this is a convenience function that just, yeah, it does lerp for each channel. And then it masks the results together. So first it does a lerp operating completely on floating point value. So it's a float, and it's a float. And the result is a float that is then converted into a 5, it's converted into an integer basically and masked. And then we mask together, we OR together the colors. So all this operation is like, yeah, it's super slow. And then the actual lerp is this function. So this is sort of the math behind linear interpolation. So we have one value and we have a second value and we have a scaling or a mixing factor, like how much of the one side or the other you want. Yeah, and as I said before, this is very naive and simple approach, but I did it just to be able to look at the result and see how it looks. And to be fair, it doesn't look like crap. It looks pretty good, but it's just very slow. So then you might ask, yeah, well, how slow is slow? So let's show you. So I actually added some profiling code. Just an off-topic question. Which, with your USB mod, with the breakout connector, you're able to close the case and still connect through SWD. Did you leave the battery disconnected in the case? Yeah, so in my case, I haven't actually screwed together the unit. Sorry, wrong screen. There we go. So in my case, I have this mod with a USB-C connector, and the thing is that yeah, so the battery connector, if you connect it, I mean, it should work, but the problem is that you might crash your device. Like it might get stuck in an infinite loop, or it crashes for some reason and gets stuck, and then you need to reset it. And with my mod, that is only rerouting the SWD data and clock pins. I don't have the reset pin exposed. So if you want to do this, yeah, be prepared to open it up once, or it might not be the optimal solution. Ideally, you should use a more complete breakout board with more where you can expose the other what's it called again? Yeah, more pins basically. So you could use, for example, the high-speed RX and TX pairs to be able to route the reset pin as well. So yeah, that would probably be a better idea. But I didn't have such a breakout board at hand, so that's why it is like it is. Yeah. All right. Yeah. So let me just put it back together again. Yeah. I mean, the nice thing with the USB mod is that it's zero cost basically, and there's no case modding involved at all. You just put it together and it's done. If you are able to. Oh, I'm trying to put back the case together. There we go. Yeah, there we go. Okay. So going back to the code, yeah, so I added some profiling code. So I'm gonna rebase this patch. Yeah, it's only one commit. There we go. So now that is rebased. And so a few days ago, I added some macro. Let me show you in main.h. So I added this profiling. Let me just close the window. There's a lot of noise. Okay, so I'm just going to go through this code very quickly. So I enabled the RTC, which is a real-time clock that ticks at 32 kilohertz, more or less. I tried to get the external RTC clock to work, but for some reason I was not able to. So I'm using the internal shitty one. With it has quite bad precision, but it is enough to get the. I mean, it is a relatively high speed clock, like it's 32 kilohertz, which means that it's high enough to get precision timings, so more than like 1 millisecond. And then I'm using the RTC calendar basically to request how many ticks have passed. So whenever you want to profile, you do the profiling init, and then you do the profiling start, and then finally a profiling end. And then you can do a profiling diff between those values. So I can show you how this is being done over here. Yeah. So as I said before, the Game Boy code is more suitable for us today because it scales in 2 dimensions, and the code fits in the internal flash, so we don't need to flash the external flash all the time. So let me just prepare a Game Boy ROM. Let's take this one. Yeah, that looks pretty good. All right. I need to power the target to flash it. Nothing strange. Okay, so let's attach the debugger, and we can print the log buffer. And here we can see that the blit time takes around 900 microseconds, so 0.9 milliseconds, and that is pretty fast. And the way we know that is because in the blit function, I have added these macros here: the profiling init and start, and then the actual processing, and then the end, and then a print. The matrix has you. Yeah. Hey, guy. Hey, Nate. Yeah, so that's how profiling works. So because profiling is always a little bit, I don't know, it's always a little bit messy, I thought it's better to just make macros and then you can just use it like this. So yeah. So this was the screen blit. Yeah. So I thought we had a different. Okay, so it's always this one. Yeah. Okay. So let's try to integrate this code. This will be quite a lot of work, but it has to be done. Nice. So that's the way to get like system millis. Yeah. So this gives us resolutions of 30 microseconds. So one step or one tick is 30 microseconds, I think. So as I said before, it uses the RTC clock that ticks independently. I could also use the system clock, I guess, but yeah, microseconds, exactly. So because I wanted to have a little bit more resolution than just milliseconds, because then it might be like, oh, it takes 0 and now it takes 1. Okay. And you don't really know how long it actually takes. Yeah. Okay, so I guess I'm just gonna copy this function and make a new one. So let's call this bilinear. And yeah. Obviously, there will be a lot of things to adapt. So, I guess to make my life easier, I guess I can just... I mean, I should be able to just copy the parts I actually need. So, this, for example, or here. That's a lot of code. And I just want to check if we do anything afterwards. We do the tear down, which probably frees some data. Yeah, exactly. We don't need to care about that because we don't want to use dynamic allocations anyway. Thanks for the follow. Okay, so what are we doing here? We need the image t struct. That probably makes sense. Then we can, I'm gonna do like a rough integration, and then we can make it cleaner as we go. Rectangle Roy. Yeah, I guess we can just skip that one. I think. Do we actually use that? Exactly. We can just set that as null. So just call it void. Or I guess I can import it. It will be faster. Gonna need this one as well. Image hint. What was that again? Right, that is telling us to use bilinear. So I mean, now I'm just making like a very rough sort of dirty import, and then we can clean it up later. Oh, wow, that is a big one. Okay, so now we're that far. What can we do now? It is doing some logic, and then it's allocating a buffer, but we don't want to do that. We need to do that in a static allocation. So let's just do that later. It's actually no, we probably don't even have to care about this. So I'm just keeping the code here so I can put a breakpoint here to see if we actually end up here, but we really shouldn't, I think, because here it checks if the hint is the RGB channel first, or if the hint is color, apply color palette first, right? And we are probably not going to do that. So yeah, let's just skip that for now. And then we don't even need to have that. And then we have the row data setup. Yeah, I'm gonna need to import that function as well. And the only thing that does is it's basically setting up a frame buffer. Yeah, so let's weed out this whole chunk. Yeah, we really don't need. We don't need like allocating a buffer, but we need something. So let's put a to do there. I just want to basically see how far can I get until it builds, and then we can optimize it. Then here's some sort of alpha palette. We don't need that. Yeah, okay. I think we're getting close. Maybe I can actually compile this. This is gonna be interesting. So let's see if it compiles. It actually compiles. That is really cool. So now we're basically at step 1. It compiles. So let's try to use it. So we need to do some setup. Let's just do it like this. Yeah, okay, so how do you use this function? To write to the screen frame buffer, do you need a specific bytes per pixels? What format does it use natively? Yeah, so it actually supports two or many different formats. These are the native formats it supports. So this is the LCD driver, what kind of pixels it can read. And so for the NES emulator, I actually used this format. It's a lookup table based format. But the problem is with the lookup based, so the nice thing with the L8 format is that yes, you get a lookup table and it's very efficient. The problem is once you start blending pixels, your in between pixels end up being having a value that is not in the lookup table. So I actually need to go over to the 565 format. And the actual LCD, the physical LCD, it is only a 565 if I remember correctly. I don't think it has more data pins. Like the actual physical display doesn't support more pixels. But now that you ask, I'm honestly not 100% sure. We can actually check that with the traced out stuff. So here you can see the number of connectors. So we have 33 pins on the display. So this is the display data connector, and this is the power connector for the yeah, whatever it's called, display. Nice. I was wondering that because of the 1 MB RAM constraint. Yeah, exactly. So yeah, to be efficient in RAM, we can use the L8, but the problem is that sadly we don't get the nice. We can't do nice blending or scaling with the L8. We need 565 to do that, unfortunately. But if you're making your own game or you want to optimize and so on, yeah, you can definitely do that. Mm. So I just wanted to sort of verify here if we have all of the data pins are actually connected to the LCD, and now I actually can't remember if that is the case or not. So I think we have it configured in 565 mode. Yeah. Oh, it's actually in 666 mode. That's interesting. I honestly don't know if that's right or not. But yeah, in any case, we are operating at 565 with 565 buffers. So yeah. Okay, so going back to the code, it compiles. That's very cool. Now we just need to call it. And then we need to adapt the buffers and so on. But yeah, we're getting to that soon. So yeah, so this is the old loop. So let's change that. So this is the small function prototype. So let's call it. So first of all, I guess we need to set up a destination image struct. And yeah, let's just do like this. We can do with. So this is the frame. This is the actual frame buffer. So that is actually 320 by 240, and the BPP is 2, and the data or pixels is this one. So we have double buffering, so we are swapping between two buffers. So now we have that. Now we have a destination image. That's cool. And then we have a source image. So that is where we are copying data from. And the truth is that the source data is in... No, actually, this is the Game Boy emulator. Yeah, that's good. So the difference between the Game Boy and NES emulators are, at least in this case, that the NES emulator has, or it's exposing the native lookup table based frame buffer that the emulator is using internally. But in the Game Boy case, it's actually applying the palettes. So our source frame buffer in this case is actually a 565 buffer. So I just removed a little bit too much code, so I can't remember how this is done. Yeah, there we go. So let's set up a second image struct, call it source image, and actually we cannot do like this. So sorry for if you can't really see on the right side, but yeah, I'm gonna try to think about that. Okay, what are we doing? So this is a global. Okay, there we go. Yeah. So let's do like this and fill in. That is still. Thanks for the follow. Yeah. Sorry for the mess. But yeah, let's just hardcode that. And so now we have two image structs. One with the source image, where the emulator is outputting its new image, each frame. Okay, and then destination start. So in our case, we want to blit at a padded offset. So it's our H pad. And then we have the Y start. We want to start in the very top. And then we have the X scale. So these are floats. So let's prepare those. X scale. So let's do like this. We have a float cost for the destination width divided by, let's just do like this, divided by the source. So maybe this needs to be swapped. I honestly don't know. Let's figure that out later. And then do the same thing for the y. All right, and then it's 8. So now we have two scaling factors, one for the x scale and one for the y scale. And then we have nothing here, the region of interest. And then RGB channel, let's just do -1. I'm assuming this is a bit mask for the channels that we care about. And alpha, I don't know, let's say 255. Palette, let's say 0. Then alpha palette, say 0. And then what was more? Hint. Yeah, I don't remember what that was. I think that was the scaling configuration. Right, so we want the bilinear. I wish I had a device like this in the 90s. Yeah, I guess so. And then the callback, let's just not do that. Destination row override. Nah. Okay, I think this is it. So this will obviously not work because I stubbed out some allocations. Yeah, we can remove that. Oh shit, I'm changing in the wrong line. So here we have something. Row buffer. So it's allocating a scratch buffer that is image row size. So let's just do like this, call this a row scratch buffer. And let's do this like 320 times 2. Or actually it's 240. So it's a full, no, actually it is 320. So it's a full width row. Yeah. Let's just do it like that. Cool. It's a little bit ugly, but whatever. And then here is the second one. So here it's actually allocating. Yeah, right. So I don't think we need this. I'm going to put a breakpoint on this line just to see if we end up here at all. So yeah, this is going to be interesting. Right, okay. So another thing is that we need to use this blitz function as well. So I'm gonna do like this, and yeah. So this is the setting up the callbacks for the emulator. Okay, now it's actually a little bit more interesting because now it's actually trying to link, and it fails. It fails to link because of many reasons. Let me just scroll up a little bit. So as you can see here, first of all, we have the fast floor f function that we don't implement. And then there's a bunch of macros. So let's try to figure out where these macros come from and how to implement them. So first of all, fast floor f. We did a quick look at this one, and I sort of gave up on it quite quickly. So I guess I want to see implementations of this. I guess it's this one. Ah, wow. Okay. Let's just say thank you does this even work on this architecture? Well, we'll see. This will be interesting. So I'm just going to put those here. So I'm guessing I'm getting errors. Yeah. Okay. So I need to expand this macro. Okay, it actually builds. Cool. So now we need this macro. There we go. And then we need this macro. Maybe it's in the same file. Yeah, it was. Cool. And then let's build min. Oh my. Wait, what? Why doesn't it just do a mem copy? Oh well, whatever. Let's copy this little piece of code as well. My scroll wheel is gonna wear out. Holy crap. Okay. Whoa. Yeah, well, let's just we can remove code later. Oh my god, that did not build. So okay, let's weed out what we don't need. First of all, yeah, let's kill those. Where does this come from? Okay. If it's not the black background, well, let's just remove it. Okay, so if we have an alpha palette, well, we don't, so we can just remove all of this. Then we're gonna need to remove that. Then grayscale, no, let's just not do that. Hello. Yep, welcome. Yeah, and then we can probably remove all of this. And then, yeah, there we go. What are you making? Okay, so I'm currently I'm integrating a scaling algorithm to be able to scale between different resolutions. So the issue is that the LCD. I just realized that my voice disappeared. Sorry. Yeah, so the thing with the Game & Watch is that the LCD is 320 by 240, and we need to scale up the Game Boy frame buffer with a non-integer factor. So we need bilinear scaling so it looks nice. So yeah, that's what I'm doing. So let's build and see what fails. So I guess I removed a little bit too much. Actually, let's just... Oh, wait a minute. I removed too much. So our destination, yep, and the source is 565. I guess I'm gonna have to re-import this. I removed too much. Okay, it's always fun to import code that you haven't written yourself. It's always sort of a challenge because there are so many unknowns. But yeah, let's see if we can figure it out. So the destination is 565, so we can remove that code. And then the source is not binary, it's not grayscale. Is this buggy or am I blind? Because it doesn't make sense. There it's grayscale. Now look at this, it's the editor that bugged out. Check it out. It didn't realize that that there were multiple cases. I guess it's just too much code for Visual Studio Code to handle. Okay, there we go. Because we only care about 565 on top of 565, nothing else. Oh my god, that is a lot of code. So let's go through it. If the RGB channel is less than 0, okay, that doesn't make that much sense to me. Well, to be honest, I'm gonna remove this call. I think, because yeah, it's copying the row. Yeah, this is a mem copy. This is a mem copy. Let's just remove it. There's no use to, no reason to sort of try to import it and be nice. Because we only care about what we care about. Which is 565 on top of 565. So let's just remove that. So let's see here, this one. Yeah, so instead of doing that, we're gonna do a mem copy where we have a destination, dst. Did I call it? Let's just copy it from here. Destination image, right? Destination image dot pixels. And that was a byte. Yeah, so this is really important to see what kind of data type it is on the pointer. Oh, I came back to see Anya raided someone. Hello. Oh, nice. So I guess I got raided. Welcome everyone. So anyway, destination pixels. So this is the pixel 0 top left. So we need to offset this with the destination x start times 2. And then we also need to offset this with a which row we are active, like the active row. And I guess that's the dsty. Yeah, so dsty times the number of pixels, so 320 times 2. So this is really hacky, and I will change this to not be hard-coded later on. And then for the source image, we take the row data and pick out the buffer, which is, let's see here, it's this one, yeah. So we just do like so. And then we don't need any offset because this buffer is already prepared for us. And then we need a length, and that is, yeah, I guess, this is so cool. Oh, nice to hear that. Okay, let's see here. So end minus start, and then this times the size of the pixel, which is 2. So this is really hacky and not very nice to do, but yeah, let's build and see if it compiles. Okay, it does not. Get row buffer. So we need to import this function. So yeah, okay, it's just a wrapper function, nothing strange. So let's just put that here. Okay. Undefined reference to image size. Okay, let's see how that is implemented. So here we go. Okay, so this is how many, this calculates how many bytes image is. So it takes the size of the, so the width times the size of each pixels, and then times the height. So I guess I will need one more macro. Okay, it's not compiling. Conflicting types. Okay, do I already have this? Oh, maybe I need to put it higher up. Okay. So I just need to expand some macros, or import some macros, I guess. So it was the 565 and binary. Okay. So yeah, let's just put that here. And yeah, let's just take both of them. So okay, it's close, getting closer. There are some macros within macros within macros. So guess we need this. So just to explain what I'm doing, I'm importing an image scaling library into the Game Boy emulator for the Game & Watch. So I'm doing this because I want to be able to scale it so it looks nice. Yeah. Okay, getting further. Need a log 2. Okay. How is that implemented? Oh wow, that is some interesting math. Guess I should put that here. Yeah, I might just as well take these. Who knows, maybe I need them. Okay, it actually builds. So let's see if it runs on the device. Okay, so this is a little bit scary. Why does it work? It shouldn't work on the first try. Let's just see. Okay, it actually takes 10 milliseconds to scale. That is a long time. That is a really long time. But I think this actually means that it works. So check it out. This is actually being scaled with the bilinear algorithm. And the porting seems to work. That was very interesting. So the question is, why is it so slow? Could it be that we need some optimization hints? Yeah, exactly. Like I was not expecting this to work on the first try. Like obviously I had a lot of build errors, but I was expecting it to be like, the colors were all garbled and messed up somehow, but no. Um yeah, I'm building with O2. Um so yeah, the question is what is it that takes time? Um because 10 milliseconds, that is a long time. It is really a long time. Um, we will not be able to use this for the other scaling, for the other emulator, the NES one, because yeah, that is a lot of time. Um, so let me just let's see here, disable the profiling. Yeah, I guess I can do like this, and I will flash it again. Okay, and then just gonna let it run for a while, and then we can look at the log. So yeah, so actually the Game Boy emulator, it's so fast, so I'm actually getting 60 FPS even though we are spending 10 millisecond of our 16 millisecond budget on scaling. Um, yeah, so let's try some other uh, ROM. Um, we can try that really really cool demo. I think it was Pocket. Right. I mean, I've had so the Game Boy emulator is so fast, so it actually runs at like 200 plus FPS, and we need to limit the FPS. But that extra time is now being used to scale, and scaling takes um like 10 milliseconds, which is a lot of time. Yeah, so this demo is it's really far out. It's using some really, how should I say, it's pushing the device to the limit, so I guess that's why it looks so messed up. So if you play this demo on a proper emulator that is like emulating stuff correctly, it looks much better. Uh, but it's a good test because it lets us, you know, test the hardware or test the emulator. So let me just print the log buff. So it's actually showing us that it's running at 60 FPS. It's not dropping any frames. Um, and when I look with my eyes on the device, it looks really good. It it really looks good. I gotta go. I have course. Okay. See you next time. Um, yeah. Thank you. Yes, actually, this is a good this is some good progress. So I managed to actually import that code and run it. And yeah, I guess the X offset is wrong. Maybe it is 2 times as much as it should be because of the bit bytes per pixels. I don't know. But yeah, this is definitely cool. Yeah, let me check. Um, Here we go. 160 by 145. Yeah, that's right. And is this demo possible with a stock RAM, or have you upgraded the RAM in this one? Okay, no, so this is with a stock flash. So I can show you on the camera. So this is no hardware modifications. And here we go. Yeah, so this is my second unit where I have, let me just, all right. So now you can see it a little bit more clear. So this is my second unit, and this chip right here is the flash chip. It contains 16 megabyte of storage. So it's not RAM, it's storage. But yeah, theoretically, you can change this to a PS RAM and actually upgrade RAM, so you get more RAM. But the problem with that is that RAM is not persistent. So once you reboot or lose power, you lose everything that is on the RAM. So one cool thing that you could do is to put like a PS RAM that would give you like 8 megabytes of extra RAM, and also fill that with data, and that way you get like 8 megabytes of data and RAM. But that requires some work, but it's not impossible. Like the chip is actually designed to handle that. But again, the problem is that once you lose power, you lose the contents of the RAM. So it's not ideal. But like one solution that you could do is to have PS RAM and then prepare that with a bunch of ROMs and so on, and then you get both storage and RAM. But again, it will not be fast, but it is RAM, so yeah. All right, so I'm pretty happy with this, and it's actually in 30 seconds. Yeah. Let's see here. Yeah, so if I want to commit this properly, I should put this in a separate file and clean it up a lot. uh, there is a chance that I'm wasting time doing something stupid, and that we can optimize this. Yeah. So let's enable the profiling again in main.h, and then we go to the memcopy. I'm just gonna comment this out just so we're 100% sure that we're actually running this code. Oh yeah, let me move the camera a little bit, or move the unit to the camera. There we go. And yeah, indeed, it looks like it's dead because I'm not updating the frame. I'm hearing the music. So yeah, this memcopy does indeed copy the row, and I almost got it right. I guess the uh, let's see here. Yeah, something is a little bit off with the offset. The horizontal pad is a little bit messed up. So yeah. So I'm gonna debug that a little bit. So let's put a breakpoint in main.gb.c on line 578. So this is where we do the mem copy. And oops. Okay, so we want to print or render 293 pixels for some reason. Oh, are you applying filtering to width? If you are, it shouldn't be necessary since Yeah. Well, let me think. Um, so it's all about aspect ratio and so on. Um, so the problem is that um, here. So we have 160 and 144. That is the aspect ratio of 1.1. It's like almost square. And the screen is 320 by 240. So it's a quite different aspect ratio. And if you look at how a Game Boy actually looks, um, the screen is basically square physically. So with the NES and with the NES emulator, um, you actually want to make the pixels a little bit wider because the CRT pixels are not square. Um, yeah, now I don't find any good source, but I read somewhere where someone explained in detail that yeah, your PAL pixels are actually slightly wide, um, which means that yeah, you want to scale it with some widening. Um, but in our case on the Game Boy, we have square pixels. Um, yeah. So I guess again, if we go back to the code that's calling all of this, that sets everything up. So yeah, here we have chosen 266 as a width and chosen 240 for the height. And I guess yeah, so the height is a little bit odd because we're going from 240 from 144. So that is a yeah, this aspect ratio or this scaling factor basically. We should actually be able to print that. Um, wait, what? Yeah, I mixed up the way you want to scale stretch NES with normal scaling. Yeah, exactly. No, so I mean it's nothing. It's not strange to mix that up because this is a little bit strange because for the NES we actually want to do stretching, but for the Game Boy we just want to scale with a sort of non-integer factor. Because when you scale with an integer factor, it's extremely easy. You just copy pixels. But going down, that is, of course, a little bit harder. There you want to blend pixels. Um, but again, so this is the width and height we are targeting. Um, so we have 266. So yeah, I guess I could just clean this up after stream and try to understand exactly why. I think the padding is being applied twice, basically, because now I'm not applying the padding. So the X start, destination X start, um, that is the padding, right? Thank you, GB. So it's a little bit annoying that even if you build with -g GDB, you still get values optimized out. It's a little bit of a pain. And for some reason, the backtrace is borked. I don't understand why. Regarding Game Boy scaling. Ah, nice. Let me open that up. Okay. Uh, okay, let me try to understand what's going on here. So horizontally, we just double it. Vertically, middle 2/3 of the image are doubled. So are you saying it's bilinear in the horizontal axis? With a factor of 2/3? Or 3/2, I guess? Because, yeah, I mean, the biggest issue is that we have the 144. If we go to this, so the height is 144. So if I double the height, I get 144 times 2, which is 288. And we have only 240 pixels, so that means that we need to crop. So I don't really understand how you're able to get an uncropped image. It really deforms the picture. Yeah, you're right. You can see that on the hearts. But how are you able to double the vertical lines or horizontal lines? Because shouldn't it be 144 times 2, which is bigger than the screen? Or what am I missing here? Horizontally, columns are double. Oh, sorry, I'm not reading correctly. I'm being stupid. So okay, so what you're saying is the columns are just doubled in width. Okay, and then vertically you are scaling 2/3. Okay, now I get it. So uh, I guess it's like this. Okay, so we end up with 160 times 2, which is 320. And then on the vertical axis, we have the 216. Now we can try this out. Now I understand. I was just being slow. Sorry. So right. Yeah. So instead of this, wait a minute. Here. Right. We can write 320 by 216. Right. Right. So I've messed up the H padding. Yeah, right. That should be 0. One more time. There we go. So as you can see, there is a slight black border in the bottom. And sorry for the camera being so slow. I'm gonna change the frame rate. Oops, I choose the wrong screen. Anyway, now you should be able to hear me. So I changed the camera settings so it has higher frame rate, and so you're able to see 30 FPS. And as you can see, this is really nice. It looks pretty good. Yeah. So I'm just gonna mute and let's put a breakpoint and check out the log. So the blitting takes, yeah, like before, it takes 10 milliseconds. And I think we can do better because we only need to scale vertically now. So, but this is interesting. So actually, what I'm gonna do now, I'm gonna break, and then we can look at a frame in GIMP. So I'm just gonna play for a little while, and then I'm gonna reset it. Until we get an interesting frame. I think the one where it rotates or morphs or whatever you can call it is a good one. This one. Yeah. I'm gonna mute. Okay, here. That's a good frame. So I'm gonna dump the memory. I'm gonna dump the RAM of this frame, and then we can look at it. So mon dump image frame. I forgot where the frame buffer is located. Yeah, okay, so let's just dump that. Mon dump image. Yeah, just 1 second. Okay, so this is how it looks. I'm just gonna open the source as well. So now I need to know where in RAM the emulator's buffer is located, which I forgot. Actually, the easiest way, nah. yeah, I'm lazy, so oh, it's actually, it might look like a null pointer, but it is actually not, because the memory is located at address 0, because I asked it to. So I'm gonna need to dump that as well. So let's call it like so. And I don't know how big that is. Maybe that big. Yeah, here we go. And it's not 320, it's 144. No, 160. Yeah. Okay, so now I will show you GIMP. Yeah. So this is the raw frame buffer in memory, and this is the scaled version. So as you can see, the vertical lines are a little bit blurred. So here's the original, here's the scaled one. There's something that I don't quite understand. Like, isn't this supposed to be... I need to measure a little bit. I guess. So here we have 160. And 160 times 2 is 320, right? Yeah. Oh, right. Actually, I'm not doubling. I'm using bilinear filtering for the width as well. Yeah, okay. So actually, for this to look good, I need to do this in 2 steps. So first I just double them in width so that I get like nearest neighbor scaling in width, in the width axis. And then in the y-axis, I can do bilinear filtering, I guess. Because this looks a little bit blurry, right? So JTH, if you're watching, this is how it looks directly from the frame buffer. But if you look at the video, like this is the actual LCD, it looks really it is a little bit soft, I guess. Yeah, but at least now we have the tools. This scaling is yeah, it's not. I mean, it's not super fast, but it's not too slow. All right, we're relying on the fact that usually top and bottom are less used. There's usually scoreboard and stuff. Some games may suffer, some will be okay. Original idea was to get away without bilinear completely. Oh, okay. So how would you do the... yeah, just doubling on the x-axis, right? But what about the y-axis? That is a non-integer scaling. Because the... Or are you like copying every... okay, so you are injecting one extra every third row, or every second row you get one extra row. I get it. Okay, I get it now. Top and bottom 1/6 are not scaled at all. Aha. Now I understand. Okay, because now I see it. This angle is like much weirder than this angle. This is perfect 45 degrees. Okay, wow. Now I understand. I'm sorry, I was being like really slow today, but now I get it. No injection there, just seems good. Yeah. Okay, let me open this in GIMP and I can show what my understanding of it at least. Let's hear. Edit, paste. There we go. So this part here in the top. Oh, let me switch. So this part here in the top, that is there you don't do the y-axis doubling, right? And here it's just completely doubled on both axes, right? That's why we get this nice 45 degree thing. Like there's no aliasing at all going on here. And then here in the bottom we get the wide hearts and the wide fonts because we're not doing the y-axis doubling. Yeah, now I get it. It looked so good that I didn't realize, to be honest. I needed to think about it, and you needed to help me for me to realize. But yeah, here you can see it's not the same angle as here. But yeah, like you say, if you have scoreboard here in the top and in the bottom, it doesn't matter. It will look good. So yeah, this is definitely a good idea. Is this what they do in original firmware? So in the original firmware, they do bilinear scaling. We have verified this, and they stretch it in the x-axis. They make it wider. But yeah, with this algorithm, we can definitely do the stretching. So let me make a commit of this. Of course, this is in the ugly hacky branch. So let's do like this. And also I need a license is MIT. Okay, so I'm gonna put this in a separate file just so I don't mix up stuff. Then let's go back. Like so. So I get the dirty changes. So this is a good trick if you don't know about it in Git, that you can undo the latest commit and still keep all the changes in your working copy. So this way, wait, what is this? Oh, I maybe went a little bit too far. Okay. But yeah, let's unstage this and put it back in a different file. I'm just gonna put all of these structs and definitions. Yeah, okay, so let me just clean up this a little bit. Yeah, so just an update. I have implemented or imported the bilinear scaling code from this OpenMV project, and it actually runs on the device. However, it's not super fast. Wait, what just... Did I break it? Oh man. I should never clean things up on stream, because I always mess stuff up. Anyway, so yeah, it's this bilinear scaling algorithm that I have imported. It does a lot of fun, fancy stuff. Yeah, this should have worked. All right, let's just remove this. Yeah, here we go. Okay, okay. Now we can flash it again. No? Wait. Okay, I feel like I want to hide under a stone. I don't know what's going on. It worked just a few seconds ago. Just gonna do it like this. Maybe it's a stupid include. Missing includes or something. Okay, it was a stupid missing include. So stacksmashing. If you take a look on the stream, it's black. Well, fuck. Why is it black? I've messed it up. Oh my god. Why is it always like this? How disappointing. So in case you're not aware, yeah, there is something called git reflog or reflog, however you want to pronounce it. It shows you where you were on your git stuff. So just a few seconds ago, I think we were probably here. So I'm just gonna try to build that. Ah yeah, here we go. Git reflog saved us. So stacksmashing again. If you want to check it out on the stream, now I'm showing the bilinear scaling that is running in real time on the device. And yeah, that's how it looks. And if we enable profiling, we can see that I'm just gonna mute it. Then we can see that it does take a while it takes, oh, this one is way faster, so now I am confused. I'm probably looking at the wrong thing. Oh well. No. Main GB and split. Okay. I give up. I give up. I'm gonna check out this one again. And I guess we have to do it the boring and methodic way instead, and actually look at what we're doing. So did I change this? No. Oh, why is that? So once again, we go into the bilinear function. This looks right, and we go into this one, which is in a different file now. Yeah. And did I comment out the mem copy or something? No, it's there. Strange. There's a bunch of warnings. I want to get rid of all the warnings, but I haven't spent time to do that. But it will happen someday. Because it's kind of hard to see when you have an actual issue, when you have this many issues or warnings. Yeah, so it's playing music, so something is just wrong. But anyway, here is the bilinearly scaled version. So yeah, it doesn't look, it looks soft. And yeah, this method by JTH is really interesting. I might actually try to implement that now. I just want to get this working again. I'm really sad that this stopped working now. I don't understand. So okay, so it's playing break main GB line 211. So destination image, yep, looks fine. Source image looks fine. And yeah, just as a sort of a reminder, when you check for null pointers, that's not always a good idea, because in this case, our pixel buffer is located at the null pointer. So yeah, it's kind of interesting. Anyway, so this is the source and that is the destination. And then we have the X scale and the Y scale, which is optimized out. Thank you. But yeah, we can print it like so. 1.5 and infinite. Okay, maybe this is our issue then. With 1 is this. Come on. How can that be optimized out? Okay. Yeah, we don't use those. I don't know. I'm gonna try something really, really nasty. Just holding down Control Z until just before I copied out the code. There we go. And then let's go to the makefile. Remove that file. Okay, now it's working again. So now, now I'm back again and can actually commit this. Yeah. So I have no idea really what happened, but yeah. Okay, so let's go back. Let's get back at this code. So I'm just gonna do like this. Hack. Then let's look at the git log. Yes, perfect. Now we can actually fix it. So I'm gonna move this code out. All of it, like so. No, I'm still gonna need some definitions. Put that back. Bilinear.c. Yeah, there we have all of this stuff. I mean, I didn't really change anything, so let's just remove that and draw image. Yeah. Right. Yeah, I get some multiple definition errors now, which is expected. So now I'm gonna remove this. And then this should go into the header file. Okay, this time it worked. But I get black pixels when I have it in a different file. Okay, so that is kind of annoying. So what could that be then? So when I have when I split it up into different files, I get black pixels. Could it be some stack issue? Am I running out of stack memory? Nah. Could it be the inline stuff that doesn't work? No. This is a mystery to me. This is a mystery. What if I move this into this file? This is not right. Why am I having so many problems? Okay, so it's writing to the correct frame buffer. That also looks good, so I don't understand this. But yeah, it's just a lot of zeros, so it hasn't updated any pixels. Don't understand. So yeah, this looks good. Could it be something with the memory allocation for the row data, row buffer? Yeah, this one, right? Okay, so that is full with zeros for some reason. Yeah, it's constantly black. And this is the frame buffer of the Game Boy. So that is obviously full with stuff. So yeah, I wish. I want to improve warnings, of course, but it's gonna be horrible. Where do we have the warnings? Shared variables that are not declared correctly. Yeah, could be. Let's see if this even builds. I always forget the good warning. Just 1 second. I always forget how you set up the warnings. There's the pedantic as well. But yeah, it's gonna be a pain to figure out what actually. Okay, wait a second. Thanks. Here we go. What? So I'm just gonna touch the file that I care about, and then we can build it, and we see a few warnings. Yeah. Joined late. What is happening right now? Okay, so I have imported the algorithm for a bilinear scaling that is optimized for the microcontroller that we're using. And right now, I'm trying to figure out what's wrong. When I have the algorithm in the same file as my other code, it works fine. But I wanted to split it up because it's quite a lot of code. So I put that code in a different file. But now I just get black pixels. So I'm trying to figure out what is going on. So this is a fun debugging session. I'm a little bit annoyed because it doesn't make sense. But I'm obviously doing something wrong. So let's just yeah. So it's in this function. So IMlib draw image. It takes a bunch of 2-frame buffers basically with configurations. Yeah, frantic refactoring is happening exactly. So that always ends up well, right? So I guess yeah. Okay, I guess I can break at this line. Break bilinear line 384. Oh, this is interesting. So I don't end up there. I'm guessing my parameters are incorrect. Okay. Just gonna rewind a little bit just to make sure that. Okay. So this is my entry point. I'm calling that function. And that is actually happening, but we don't seem to actually end up in the while loop. So are we doing a early return? So maybe something is wrong with the, yeah, let's just step one line at a time until we return and see. Oh, wait, didn't we return there? If alpha is 0, return. Oh, but alpha is not 0. Did I change the order of the arguments or what? So wait a second. This is weird. So I'm just gonna put this in the header file because obviously you should do that. What? Now it's working? Okay. So, I mean, this is not really surprising, I guess. Okay. Okay. So, lesson learned. Don't be stupid. Always put your function declarations in the header file and don't rely on the compiler to sort of figure it out. Because I believe what happened is that it mixed the data types of the arguments, so they got jumbled around, and for some reason I got a 0 in the alpha when it was in fact not 0. So that is what happened, and now it looks good again. So yeah, don't be stupid. That's a good motto. So I'm gonna add this to the change list. I'm gonna add, did I even make a change here? Just some white space. And then what did I do here? I removed all of that code. Yeah. And then the mute, I shouldn't commit that. Yeah, that looks good. Cool. So, oh yeah, and the make file as well. Some extra warnings. And then we can squash this. So squash, squash, squash into this one. Yeah. So just to make sure I'm not doing anything horribly horrible, just slightly horrible, we have one commit that adds a file with a bunch of stuff, adds another file with a bunch of stuff, and then we change main where we add bilinear, and we add a new blit function, and we change it, and we do some changes in the make file. Looks good. What's the name of that ROM? Yeah, so this is the Pocket demo. It was linked before. I might be able to find the link again. It was something. There we go. Oh. There we go. And it's really cool. You should watch it in a proper emulator. Yeah. But yeah, you should watch it in a proper emulator because it is really cool. And on this emulator, it's impressive that it's able to show it at all, I think, because it's probably using some pretty fancy stuff, like pushing the hardware to the limit, basically. But yeah, it's really cool demo. Let me just rotate it a little bit. Yeah. Okay, but now I can push this. Linear scaling. Yeah, whatever. So now I'm gonna try, so stack smashing, I will try to explain this algorithm in short. So JTH, he posted about this method of upscaling a Game Boy frame buffer to 320 by 240. And the trick is, if you just look at this quickly, it looks like pretty good. But there's something wrong, and it's a little bit hard to tell immediately what it is. And the thing is that um, the upper and lower part, like this part and this part, maybe even that part, I'm not sure, is only being widened, the top and bottom, but the center part is being scaled with a factor of 2 in both axes. So that's pretty cool. So this is not using any bilinear scaling at all. It's just copying an extra line or an extra line and a column, depending on, or the other way around. It's always copying a column, but sometimes it's not copying a line. So I'm thinking of implementing this now. Should be pretty straightforward. So let's just make some math first. So we have 240 lines and 144 source lines. So 144 times 2 is obviously too much. So 240 minus this is 48. 48 divided by 2 is 24. So the 12 top pixels and the 12 bottom pixels should be ignored. Yeah, it should be pretty straightforward. But in this case, I actually hope it is straightforward. But yeah, let's see if we can do this together. So let's implement a new blit function. What? Let's call this blit JTH. Yeah, why not? And then we can copy the original one and just improve it. Let's put it here. So it's, let's see here. Yeah, we don't really need to care that much about this. So yeah, let me just rewrite this a little bit. Yeah, no worries. So how do we want to do this? We could do this really efficiently, where we should always widen a line, and sometimes we should copy that line to the next line. So I'm thinking of doing like this. So we are iterating through the original frame buffer. We take the first pixel and then we copy it 2 times, like so. So we have 2 pixels now. And then we have we iterate more, and we have 2 new pixels and 2 new pixels, like that. And then when we skip to the next line, we check if we are in the top or bottom area, and if we are, we just continue and copy more pixels. But when we are in this area, we can simply do a mem copy of the whole previous line and just copy that line onto the next line, because it has already been stretched out. That way we don't need to do the stretching iteratively. We can just do a fast mem copy. And that way this should be super fast. So let's just we can prepare I think actually the code in the NES, main NES split, yeah, to be honest, let me just copy this code instead, I guess. Nah. Okay, let's just apply ourselves and use our brain. So we are reading from somewhere, and that is actually a 16. Let's call that source row, and that comes from here, right? So screen buff with the offset of yeah, let's have a variable called y. Yeah, maybe do like yeah, let's not hack it too much. I'm gonna put this back. Yeah. Okay. So now we have a pointer to the source buffer. And then we have a destination, which should be something similar, where we take dist. Yeah, like this. And since we don't need any padding, we can just do like this. So we take y times width. Yeah, that's destination row. So we're operating on rows. Yep. And then we increment y. And then we should have x as well. I guess we want to do like this, so we initialize it to 0 each time. And then here we I'm curious, how did you figure out where the display memory was? So the display memory is something that we set up ourselves. So this is a project that we have configured 100% by ourselves. So this is not using any proprietary firmware at all. It's 100% open source. So all of the memory configuration and pin mappings and so on is in our source code. So it's not like a SOC that is completely closed where you have to sort of reverse engineer where stuff is and how to use it. But this is actually a microcontroller with proper documentation that you can look up on the internet. Like here's the register maps and everything. It explains exactly how this processor works. So that's really good. Okay, so now we have copied the pixel twice, and we increment the x like so. Yeah. Okay, so I'm just gonna try this just to make sure that I'm on the right track. I guess we don't need this. We can do for loops instead. Okay, that's not good. So the screen is black for some reason. Are we actually using this one? Thank you. Y times... Oh, yeah, you're right. Because that's in the destination buffer. And also there should be an ampersand, because otherwise you get the value instead of the address of. Oh yeah, this looks much better. So now it's all squished. I can show you. So as you can see, the whole frame buffer is squished. So now we need to do the copying, the smart copying. Yeah, it looks really weird when it's squished. But I wonder, isn't there a stride error as well? Or yeah, it looks... No, there's definitely an error here. This is not only squished. Okay, so I have made some other mistake. Y times W1 is wrong. Yeah, but that's... Okay, let me just think a little bit. So we're iterating through the height number of pixels. And then the source row is the screen buff with Y times the width. And this is on UN16, so I don't need to do it times 2. And for dest, it's also UN16. So that should be correct. Dest row 2 times x equals source row x. Isn't this correct? What am I missing? And then the +1 here. Okay, now I'm actually... I don't know, maybe my brain is broken today. It usually is. Oh, here's the error. It has to be 320 by 240. Yeah, there we go. Yeah, now it's fixed. Okay, so check it out. So now it's always squished, and there is no error. So this looks fine. So now let's do the optimum optimization. So after we have rendered a line, a row, we check if y is larger than or equal to 12. and y is less than or equal to 240 minus 12. Then we should no, this needs to be in the H2. Yeah, otherwise this is going to be really messy. So we're iterating here, iterate on dist buff rows. Then I can actually move this up. No. Oh man. It seemed so simple in my head. So okay, let's think a little bit. What makes most sense? How do we write this code so it doesn't become a huge mess? So if we iterate on destination rows, so we enter the loop, or then we enter this for each row in the destination. Then we can check first, are we doing one of the special rows? Well, if we are, then we need to copy the previous one. Yeah, okay, I guess this makes sense, yeah. So, no, because this is the whole area. Right. Yeah, I was thinking of skipping this and turning it into a memcopy instead. So that, yeah, I guess we can do like if y and 1, we do a memcopy, else we do this. And I mean, this is a little bit ugly, but to have this copied twice. Because if we do a memcopy, it should be faster than doing this, I think. Because here you need to have like, yeah, I think a memcopy should be able to be faster. Will the destination row be correct for the bottom part? Let's think. Probably not. So I guess no. Oh, this became way harder than I thought. You were right, stack smashing. So in the trivial case, in the bottom and end part, no. This is such a whiteboard whiteboard anxiety problem. It's not that hard. Just keep a counter. Yeah, I guess so. Yeah, let's do int source y equals 0. And then every time we increment source y, we increment this. So here we do it, and here we do it. Right. Then we do like this. That way we can move this one up a step. And destination row is always the same. Yeah, this is a little bit cleaner. So my thinking now is that this is where we want to read from. and we increment that either in the top and bottom case just twice in memcopy. No, because I want to increment the source only once. So the source is yeah, since I want to copy the line twice, I actually do not want to increment it twice. So let's just do like just row, source, row, and then the number of pixels, which will be the second width times 2. Yeah, this should be it. And yeah, I don't know. Let's try it out. See what happens. It's gonna be interesting. Okay, it's definitely not right. Maybe I should do like. So it's almost right. Is it this that's wrong? No, that was even worse. Okay, I'm gonna need a. The mem copy will mess up the stretching. So I'm thinking, y goes through the whole frame buffer on the destination buffer, right? And here we get a pointer to the row where each row starts, y times second width. So that one is correct, right? So what about the source? We are reading from a row that, oh, now I see it. Now I see it. So actually this is not correct in this case. In this case, it should actually be the destination. And it should use the source y. Okay, this makes sense, right? No, fuck. Why does this not work? Pseudocode maybe. Okay, so let me walk through it. Scale line if middle of screen memcopy y++. Dist row is 240. Oh. Yeah, but I mean, I'm doing this. Okay, let me just walk this through so I get it right in my brain. So this row is 320 wide, source row is 144. Yeah. And I mean, in this case, I am copying the dest. I mean, okay, so this is verified to be correct. This is the actual Game Boy buffer, and we're getting a pointer to each row. And the source y is only incremented either when we are in the top and bottom, or after the mem copy has been performed. Okay, and destination row is normally the destination frame buffer on the current iteration times the width of the destination buffer. So this part is also correct. And we know that it works for these cases, right? Okay, actually, this is really interesting. So here you can actually see the bug visualized. So the top and bottom are correct. That's the middle part that's messed up. And yeah. Oh, now I see it. Oh, now I see it. There we go. I forgot the source Y. Oh, no. Um, right. Maybe I should... thanks for the follow. If I just comment out the mem copy, we should see if the vertical stretching... Okay, so this actually looks good, I think. Let me see if I can zoom a little bit. Yeah, so this... Yeah, I mean, essentially, yes. Essentially, yes. Let me just swap the cameras twice. There we go. So essentially, it's interlaced because I am only rendering every second line in the middle part. But I thought the mem copy that I have here, yeah, the mem copy is supposed to fill in the gaps. It's supposed to copy the previous row into the next row. So I have source y times w2. That should be right. I mean, what am I missing? No, it should be y, of course. It should be y, because this is operating on the destination frame buffer. So let's try it out. Oh. Yeah, check it out. This looks better. Or no, maybe not. Let's see once it starts playing. Don't remember there being lines like that. Actually, this... No, there shouldn't be these lines. Yeah, for sure. I can't imagine the stress you must feel when live coding on a stage. Holy crap. I mean, I've seen those shader showdowns. I would not be able to do that. Holy crap. Okay. You know what? I'm just gonna do like this. Okay, now it's fixed. Why are you doing... What are... 260... Well, this is operating on bytes, and this is number of pixels, and there are 2 bytes per pixels. But yeah, now it's fixed. Check it out. So I'm gonna zoom out the camera. So this looks pretty sweet, right? So thanks a lot for that, JTH. This looks nice. But I wonder, I mean, it looks too good. Am I really doing it right? Yeah. Here you can actually see it because the top and bottom rows are wide. Yeah, it looks much better than I expected. Yeah, me too. I didn't expect it to be this nice. Yeah, nice effect. Now you get like a rolling, like, you know, the top and bottom is like you're rendering on a cylinder when you scroll text from bottom to top. Huh. This is cool. I'm gonna commit this. This was really nice. Yeah, check it out. Now the text is sort of accelerating. I like it. This looks good. What about delays? Can you measure it? Yes, I can. And I think actually, if I just mute, I'm gonna halt the processor and we can print it. Okay, I forgot to enable it. Let's head over to main.h and enable profiling. And then I'm just gonna halt. Let me show you my screen. There we go. Okay, so it takes 3.8 milliseconds to do this stretching, which is a little bit longer than I expected. I mean, we do the memcopy at all. Maybe the logic is expensive. I don't know. So for example, if we comment out the memcopy, just to try it out in interlaced mode. So I'm just gonna copy, that with memcopy, and then let's flash a new one, try it out. So this is interlaced, so to say. And that is way, way, way faster. So I'm thinking, what is wrong with this memcopy? Is it not aligned, or is it a slow memcopy? Is memcopy slow on this? Is this a bad memcopy perhaps? Because memcopies can be, you can optimize them a lot. Just as a fun exercise, let's implement our own memcopy. And let's just operate on 32-bit words. So This is a very standard word-by-word memcopy. Yeah, we can actually do like this. So just to explain what I'm doing here. Oh, there might be a fast EMA. Oh, definitely. We can try that. So you just whiteboard wrote. Okay, so this is actually super slow because I can hear the sound is being crunchy. So let's see what happened. How slow is this then? This is super slow. Okay, so this style, this memcopy style is not fast. Or maybe I'm not thinking straight. I don't know. Let's see if this works. Okay, so this looks perfect. And let's check the okay. So you can see that my memcopy was slower. But yeah, maybe we can do a DMA memcopy, but at this we don't really need to because we have budget for it. But what is that a color palette the emulator is using? Yes, and the palette is being applied inside of the emulator. So the memory buffer that I read from is already has a palette applied to it. So that can definitely be optimized so that we operate on a LUT source frame buffer. But I don't really understand why the memcopy is so slow. But you know what? I'm starting to think that we have an issue with the memory bus. That a memcopy is expensive because we need to read and write from a slow RAM memory. So let's compare this. Instead of doing this, let's just do exactly the same. So even odd alignment. Well, I'm starting to think that because I'm reading from SRAM and I'm writing to AHB RAM that is located on a separate bus. So the source memory is on a tightly coupled memory, whereas the destination is on a different bus. So when you need to copy from the same memory that you're writing to, it might actually be very slow. So I'm gonna try to just do this very stupid code. So yeah, that should work, I think. No, that did not work. Oh, it did work. Okay, cool. So let's just halt and check it out. This is way faster. So so let me just explain what I realized. So when I copy the pixels from the source to the destination twice, one for each line, this is actually faster than doing a memcopy. And the reason to that is that the memory is located in different places. So we had this very nice map. No, I don't have it. Anyway, I wanted to show you the different memories and where they are located in the microcontroller. But the fact is that the location where we have the destination frame buffer, it's on the AHB RAM, which is on a bus, and it's not tightly coupled. So since the source is on TCM, we can read this very quickly, and then we can write this. And I think, I'm guessing a little bit here, but I think these writes may be you can do that efficiently by just sending multiple writes and just continuing to send, especially since we are increasing the destination pointer with one each time. So that's what I guess is happening here. So actually, by not using memcopy, we're actually faster because we don't need to read from the destination. So yeah, there you have it. Let's remove the memcopy solution because we don't need it. And then we can rewrite this a little bit. We can do like this. This should be it. Let's verify. Yeah, looks good, right? So with this algorithm that JTH suggested, we're able to render with 1.1 millisecond. That is really cool. And if you think this looks a little bit garbled and strange, there's some crap. It's because the ROM I'm playing is sort of a demo scene ROM that uses, it pushes the hardware to the limit. So, but it's very cool. I like it. It's good music as well, so that's why I like to play it. And yeah, it looks really nice. I'm happy. I'm really happy. So what I'm gonna do now is that I'm gonna commit this. It's actually a pretty incredible demo for a Game Boy. Yes, definitely. I was really literally blown away when I saw it. I was really surprised. Um, yeah. Okay, so let's remove the my mem copy because that's crap. There we go. Yeah. So let's commit this. Yeah, we can leave that. And then I can push this. So yeah, maybe it's time to end the stream. I don't know. I feel that we've done some really cool stuff today. So just to do a recap, I've imported the blit code or the scaling code from the OpenMV project that has a very impressive scaling implementation. Lots of optimized cool stuff going on here. And I managed to port that. Or it wasn't that hard actually. I mainly just copied code, but yeah, I imported that into our project, and when using that, it takes almost 10 milliseconds to scale, which is obviously a very long time. But because the Game Boy simulator is so fast, it doesn't have to be a problem. And here I am showing you the original frame buffer. So this is the original Game Boy frame buffer from the memory. And this is how it looks after it has been stretched and scaled with the bilinear filtering. Okay, but this is not a wasted effort because we can use that code for the NES emulator to scale that in the x-axis. So the idea was that the NES emulator, we want it to fit the screen. And in order to do that, we need to filter it, because doing that with nearest neighbor will look really, really crap. So the 10 milliseconds that we have profiled, that is by when this code is sort of operating at the full capacity and scaling in both axes. But I think that with some effort, we should be able to only scale in the x-axis and skip the y-axis completely. But that requires me to actually read this code and understand what is going on. It's not that much code, but it's doing some pre-caching that I'm not really... I haven't read this in detail. I need to sit down and think for a while. But I think we can rip this apart, and instead of operating at these nice 2x2 matrices. Let me see. There was some really nice ASCII art. Anyway, you know what 2x2 looks like. No, I can't find it right now. But anyway, instead of looking at the 4 pixels, I'm just looking at 2 pixels on the same row. So just the current pixel and the next pixel. And by doing that, we won't have any cache issues either, because we're just looking at the current row. So because the thing is that if you're looking across row boundaries all the time, you basically trash your cache, because you're reading... I can visualize this. So memory is linear, right? It goes... can I have 1 pixel? Yeah, just to illustrate, like it... What is this? I just wanted the pixel pen. There we go. Right. So what happens is that when you operate on pixels, and a frame buffer especially, you go pixel by pixel like this, from one edge to the other edge. The problem is that if you look at the address, this is address 0, 1, 2, 3, 4, and so on, and this is on the next row, so that is far away. Hey, which means that if you need to do a matrix or sort of a convolution, where you have an origin pixel and you want to look at the pixels around that, you are looking at an address of 0 and then plus the whole row and then a few extra pixels. And the problem is that if you're on a microcontroller like we are, the memory is that is not gonna be very nice. I mean, you can... The thing is that we have disabled caching as well, because we have had DMA issues. So we have literally zero data cache, which means that every time, for every pixel, we need to do a bus access where we read one word. So we get like one small cache line, or 32 bits of data. I actually don't know how big the data bus is, but anyway, one word. And then we need to look at on the next row, which is a second word. And then when we go to the next pixel, we need to do another lookup. So we're basically getting 4 times, or at least 4 times worse performance than... I mean, it's just horrible. So by not having to look at the adjacent rows, it gets way faster. So scaling horizontally is actually relatively cheap. Scaling vertically, that is way more expensive, because you need to look at the adjacent rows, which has a large offset in the buffer. So you need to do multiple memory lookups. Anyway, going back to the recap. So the code. Yeah, so now I have integrated that code in a branch, which means that we can do linear bilinear scaling in the Nintendo emulator as well. I have not implemented that yet, but we can do that. We can actually give it a shot in a few minutes. And then the second thing that we did was to implement the JTH's suggestion on how to scale that he explained in a tweet, where we basically scale everything times 2, but for the top and bottom half, we don't scale in the y-axis. And that is what we're running right now. And that is extremely efficient. It only takes 1 millisecond to do. And it looks really crisp because there is no bilinear scaling being applied. So I'm actually really happy about this scaling. It looks really good. So thanks for that. All right, so that's it. So I don't know. I don't know what people think. If I should attempt the NES scaling as well, it could be a totally different algo for only horizontal. It's very nice. Can you explain a little bit more? Darla Dada? How do you mean it could be a totally different algo for only horizontal? Do you mean that you want to stretch it in the x-axis by using nearest neighbor, or what do you mean? You might not need to have the full XY algo. Yes. So yeah, I guess we can try it. So for the main NES, I know that stacksmashing did some work on the nearest neighbor stuff already. So we can try it out. So I'm just gonna need a ROM, and then let's flash it. Okay, I was stupid. There we go. Okay, I guess I have messed something up here. Right, because I was trying to apply the some other filtering, but let's change this. Basically, we need to take each 5 pixel of a line and bilinear it to 6. Okay, let's think about that. So you're talking about the x-axis, right? So yeah, so every 5th pixel we blend that together with the next pixel and create an extra pixel. I guess that could look okay. But I'm a little bit afraid that you might notice it, because if you have a diagonal line, just to illustrate it, let's just make a diagonal line. Oh. So if you have a line like this, then if you blend it, you get like 1, 2, 3, 4, 5, and then you get like a sort of extra bump. Where you get some sort of blending. So I don't know if it will look good or not. It's hard to say, because when you do bilinear scaling on all pixels, then you get like let me just illustrate. So then you get like soft pixels all the way. But here you will get hard pixels for 5 columns and then like one super soft. I don't know if it will look good. Maybe. So okay. Something is not very happy. Um, I don't know really what happened on this branch. Something is extremely sad. Okay, I have messed up the main file. That is the explanation. Okay, point is that it still can be simplified to rolling window algorithm, and you don't need full-blown matrices. That's what. Okay. Yeah. Okay. I get it. So now I'm just I've reverted the main file, so it's back to the stock, like what's on the main branch, just so we have a stable initial point. Okay, so this is how it looks today. I don't know really how to make it not look like crap on the camera because of the matrix, how it works. Maybe we can zoom a little bit. All right, so this is right. This is completely cropped. So as you can see here on the screen edge, there is a black bar because there are no pixels. Yeah. Okay. So let's get to it. So let's create a new blit function. Or actually, blit nearest. Let's see how that was implemented. So yeah, it is simply copying. Yeah, it's simply copying a pixel. So this is basically what we are talking about. So let's check it out, see how it looks. There we go. So as you can hear on the audio, maybe you can hear it. But yeah, it starts to lag a little bit because because we are lagging. Anyway, so in this case, we're using nearest neighbor filtering. So it's basically copying an extra. We get an extra column every n columns. So what JTH was suggesting was to perform bilinear filtering for some rows. But first of all, let's see if we can improve performance. So let's go to the main file and enable profiling. And then let's copy the profiling code from the Game Boy. Because writing code is boring. So there we go. And then we need to include there we go. So let's see what our baseline is. What's the performance? Yeah, don't mind that the screen is white. It's just init bug. We will fix that later. Wow. Okay, so 13 microseconds. That is a lot. That is a lot. I'm starting to think, like, why is it so slow? Can we make it faster? How? So first of all, is this slow? Can we make this better? So I guess for the y-axis, we don't need to do anything. We can just say y2 equals j, I think. So let's keep a track of this. So baseline, and then let's see if we can improve it. Thank you. You're right. Okay, so slightly better. Slightly better. So this tells us that this calculation will also save us some time. So let's first of all move this one up here so that we only do the row lookup each one time each row. And then we can also rewrite this a little bit. So we have the destination row like so. And the destination row is frame buffer, and yep, this should be fine. And then we can rewrite this into this. And then the question is, can we get rid of this addition as well? The H pad, we can do that by saying x2. No, that is already used. Why is it called x2? That should be x1. Because it's from the source image, actually. Let's just change that. What am I missing here? It's so compact. I need to uncompact it. Okay. So this is what we read from. Okay, so now I have messed stuff up. Maybe I should just rewrite this from scratch so I understand what's going on. And let's call stuff. Here's the issue. So we're still in lookup table. So right, I was getting ahead of myself. So this is an L8 mode. That's why it is like this. Okay. It's not broken. So let's just check our bleed time. Okay, we've improved it a little bit more. That's cool. So let's see if we can do even better. Let's get rid of this addition. Let's call this x2 plus plus. And let's do like this. Ideally, no, that's gonna be hard. I need to do this basically. Yeah, so this is gonna be interesting. Let's see how much that saves us. So again, this is because we have the RTC timer. It gives us a little bit more precision in the profiling. So instead of just saying 13, 12, 9, now we have a little bit more precision. So that's kind of nice. Okay, either it's broken or I failed flashing. Let's try one more time. Oh, right. I'm doing something really stupid here. I made a mistake. Okay, so that addition didn't save anything. I guess it's because yeah, you can do some additions for free in the instructions. So maybe the compiler found a way to get around that. So I would like to do this better. So maybe we can do that in a different way. So we have 320 on the x-axis. and we have I don't remember the source width. 256, I guess. Yeah. No, that's too good. I'm gonna have to set a breakpoint. It is 256. So why don't we just scale it? Yeah, every 4 pixel we get an extra. So yeah, we can do that. Let's try that. So instead of doing like this, so I'm just gonna commit this as a stepping stone, and then we can remove that, and let's iterate on the source instead, and if x, let's do like this, if counter is 4, counter is 0, and x2 gets copied. Does this make sense? So basically, when we copy stuff, we also check, we increase the counter, and once it is for programming in C, yes, this is C, correct. So once we have reached 4, we reset the counter, we copy a pixel, and we increase the, no, that shouldn't be increased. Yeah, let's try this. This might look horrible because my math might be off. This might be, maybe it should be a 4, I don't know. I'm too lazy to think. So let's just try it. Okay, that did not work. That did not work at all. So it even crashed. Like, what the heck? Ouch. So I'm guessing I'm overwriting some memory. Wait. I forgot to change the source pixel index. So yeah, as you can see, it takes a little bit longer time to test stuff here on the Nest simulator. Okay, now we're back again. Okay, let's mute and halt. Check it out. 5.9. So that's nice. So it's getting faster and faster. So we basically cut the time in half by just writing stuff a little bit differently. But I still don't like it. It's still a little bit too slow. So I wonder, what can we do to make this even faster? For example, if I just comment this out, like what is our actual baseline? Like if we don't do any sort of nearest neighbor at all. So this is basically just copying the frame 1 pixel at a time. I think this is way too slow. Doesn't make sense at all. Does not make sense. So I'm starting to believe that this is a memory bus issue. I believe it is. Let's just verify that. So yeah, it's a little bit hard to see on the stream, but now we have like a big black bar on the right side. But yeah, that is because we are just copying pixels now. But yeah, let's check it out. Do a printf. So now it's slightly faster, but it's still super duper slow, like 4 milliseconds just to copy. And this is byte. These are bytes. So I think we can do it much better. So let's do that. So first of all, where in the memory is the source buffer? Break blit nearest, and then let's see where it is. So the frame buffer data is located in AHB memory. So that is our issue. So let's relocate it. So what we're gonna do now is that we're gonna relocate the frame buffer data. So instead of all right, so where is that even? So I'm just gonna try something. So actually this could probably be optimized a lot. So there seems to be like double buffering going on here already, which I don't quite understand. That is wasting a lot of memory. That should... We shouldn't need to do this. This can be optimized. Let's see if this fits at all. It does not fit. If we do it like that, does it fit? It does, which means that we're just gonna do something horribly nasty. But yeah, it will probably work. So let's see if it's fast. If it is faster. I can still hear the stuttering, so it's not super fast. It is... well, I don't remember. So now we have 4400 microseconds. And we had that before as well. Okay, so... I still think that is very slow. Does not make sense. Yeah, so that is in the tightly coupled memory now. So at least it should be fast to read. Yeah, you're right, JTH. Because what I don't understand is it's very slow. Am I doing something very stupid here? Because This is essentially just a mem copy now, and a mem copy shouldn't take 4 milliseconds. So, because if we compare this code with the Game Boy code, it is essentially the same, because we're reading data and writing it. And this took 1 millisecond, and this takes 4. I do not understand. So I'm thinking if I'm doing something stupid, because that's usually the case. So I'm having 2 iterators. I have x and I have x2. That doesn't even seem to work. So I mean, if we just optimize this even more, we just say it like this. This is literally a mem copy, very naive mem copy, which operates on 1 byte at a time. Is the compiler generating B2 and putting it into slow memory? I hope not, but we can do like this, just to be sure. So I'm thinking of optimizing this a little bit and operate on 32-bit words at a time. But I still don't really understand how it can be so slow. So okay, so now it runs at least, and let's printf. Okay, so now it's actually way faster, but it's still a little bit too slow. I don't think it has to be this slow. So for example, did we have the unroll? Oh, we don't have the unroll. Maybe that is why. Okay, check this out then. Let's compare this. So this is what we have right now, 2.8, and I just added unroll loops. So let's see if that works. I think it should, but yeah, it will be interesting. Okay, it doesn't sound very good. So if it sounds bad, that means that we have bad performance. It is exactly the same. Okay, so I'm gonna try something where we increment with 4, and then let me just do like this. And then we can do, so we're basically just implementing a mem copy here. But I just want to illustrate, at least for myself, that operating on words is faster. But now we can get a number on it and see what actually happens. Okay, this doesn't look very good. All right, it's because I'm doing like this. I should do like this instead. Yeah, you're right. And I really hope this doesn't become a division, but rather a shift. But I mean, I'm compiling with O2, so that should really happen. I hope so. Okay, the music is smooth, which means that we are probably it's probably fast now. 740. Okay, so now it's basically 4 times faster, right? Yeah, check it out. So it's literally a factor 4 when you operate on words, which is not surprising because the instructions become, fewer. But now we have a visual representation. We can see the performance. We understand what's going on. So if we do some nice ASCII art. So previously what we did here with the counter was that we increase it and then we check if it's 4, which means that we have 0, 1, 2, 3. And when it is 3, we enter this. Um, so we're squeezing an extra pixel in every fourth time. So if we operate on words, this would mean that the destination will become unaligned. Um, yeah, this is gonna be a little bit ugly, but let me think. Um, I guess if you unroll it, you can get it with an even. No, it's gonna be ugly no matter how you do it, I think. Um, yeah, I don't know. I don't know if it's worth doing this in my head. So what I'm thinking is, can we optimize this and unroll it so that you get as few instructions as possible? Uh, so just to illustrate, we want to map this, rather, we want to map, oh, we want to map this so that we have an even boundary of 4 words. So we want like a barrier, like, we want to do this many word copies and not do an unaligned. Same as base64, and it with previous. Oh, I actually have never bothered to read a base64 implementation. Um, that's interesting. Um, so, or do you mean or that you? Hmm. So I wonder, is it worth doing this? Like, if the blade function is this fast, then because the thing is the emulator is a little bit slow, so we get like 70, 75 FPS or so. So our budget to do scaling is very small, actually. So unless we want to optimize the emulator, which is of course it could be fun to do, uh, we could do this. So yeah. Um, okay. Um, you're shooting for memory align. I'm honestly am just speculating or like throwing out ideas. So I want to have a few sorry, as few instructions as possible, and do aligned writes. So if I mean, that's obviously the fastest, right? You want to do as little as possible, and you want your instructions to be as efficient as possible, and you want to avoid doing unaligned reads and writes. So you could do some shifting and oring. So basically, the first word is just a copy, right? Then the second word, you I mean, we can unroll this, right? 1, 2, 3, 4, 5, 6. So I guess, does this is this even? So let's just think here for a while. We have 256 divided by 4 divided by 6. No. Why do I divide by 6, by the way? 1, 2, 3, 4, 5, 6. Okay, that's why. So I guess the last one will have to be manual. But I guess we can do it anyway. So it was a long time ago that I actually had to optimize code. I used to do that a lot before when I worked with graphics programming, but I don't do that anymore. Or like the last like 8 years, I've done other stuff. So anyway, because I was thinking of unrolling this, so yeah, it looks like divided by 5, 6 is the repetition. Ah, yeah, you're right. So, but does this even? Yeah, okay, it's not even. Okay, it doesn't matter because if we unroll this, we can make like the last step manually. Or am I thinking incorrectly? Is it actually 5? Do we actually count up to 4 before we add a new column? I think we might actually do that, right? Because what I'm doing here is I use the plus plus afterwards. So we have 0, 1, 2, 3, 4. Yeah, that's right. Yeah. But that is not. So there are two things going on here. So one is the 4 bytes per word, and the second one is the extra column that we should copy. So what we're doing is basically we want to do nearest neighbor where we have 1, 2, 3, 4, copy 1, 2, 3, 4. Or actually, I guess it ends up like this. No, it will be like this, right? Yeah, so it will look like this when scaled. And so JTH's idea is that this extra pixel should in fact be nearest neighbor filtered. So we get like a semi-blurred pixel every 5th. Does that make sense? Yeah. Um, yeah, I don't know. I don't know if it's gonna look good. I'm just thinking like how much time should we spend on making this fast. But anyway, if you just look at the speed, we are going from 13 milliseconds down to basically sub millisecond. And I'm afraid that we have to be in this area because the emulator is so slow. That was what I've inferred from original screenshots, yes. Mm. So, yeah. Okay, but let's because it's always hard to know how much time you want to budget on something. Like if you're on an obviously bad tangent, when should you abort? And it's hard to know if what we're doing right now is good or bad. But let's just look at what we have right now. So we're looking at the memcopy style code right now. So I've changed it to 32-bit words that we copy. So we divide by 4 because of how stuff works. And as you can see, this we get this big bar in the end. So this doesn't do any offset in the x-axis, and this looks very nice. And um, let's just look um, at the print, and here we can see that indeed this takes 750 microseconds. So what if we do if we inject an extra um, like if we improve on this code, we can do stuff like if counter is 4, we want to inject an extra pixel, and we can do that by doing like x times 4 plus 1 equals source row x times 4, and then we also update the destination row, and then let's see here. Yeah, this is really nasty. No, actually, this is wrong. So what I'm doing here is basically every time the counter. Oh, this is not right either. Oh, this is gonna be so nasty. Damn. I think we need to unroll this somehow. Yeah, I honestly don't believe in this. This is not gonna be good. Primarily because the iterator is working on the on every 4th byte. Yeah, this is not gonna work. And actually, I'm just gonna rewrite this a little bit to actually show what we need to do. So actually, this is not that bad. Okay. Oh, sorry. So what I've done here is, wait, I need to do this as well. So when do these come in phase? Here, actually. No, they're not in phase. Okay, here, finally. Okay. So what I'm illustrating here is that here's the source buffer, and here's the destination buffer that is getting an extra injected pixel. So what I'm looking for is when are they in phase when we use 4-byte copies. And yeah, here. Actually like that. So I don't know. I'm starting to lose interest here. I think maybe this is an exercise for some other time. But we know that we can definitely improve on the nearest neighbor code, and getting close to like 1 millisecond should be possible, maybe around 2, but it would be nice to get it really low, of course. Yeah. So actually, I'm gonna end it here. So thanks everyone for joining. It's been interesting, and we've learned quite a lot today, and also about the memory, that it really matters where we copy from and to. That really matters. And we got some nice filtering algorithms for the Game Boy. That looked really good. So thanks for that, JTH. So yeah, I guess that's it. So thanks again for joining. It's been fun, and see you next time.